Good afternoon to everybody, to our distinguished guest, and to everybody who is connecting with this edition of the INdAM Day, I should say, of INdAM Days. Good afternoon to everybody, to our distinguished. As you all know, this year is a very special year, and we have gone through a very complicated times, and it is a special pleasure to welcome all of you to this edition of the INdAM Day, which is really sort of a celebration of the Institute. And I would like, first of all, after thanking the distinguished guests, to thank the Vice President, Gioconda Moscariello, and the Scientific Council to have insisted in holding this initiative also this year in this form, as we can do it now, online, but with with great participation and with with a lot of willing to think that things will improve and that we will be able to stay together very soon in person. As you all know, the INdAM Days are thought as a possibility for the Institute to meet with local research units, to stay together, and to make the presence of the Institute be felt everywhere in Italy, because it's an initiative that every year changes its place. This year we have to adjust to the fact that the place is online, and so we keep this tradition of INdAM Day with this meaning this time, that the national character of our institute is made strong even in these very strange times we are going through. Let's say that this becomes an occasion to exchange best wishes for the new year, and to forget we are mathematicians, we don't believe in numerology, but for sure we would like to forget about 2020. And I'm sure that things will improve in the future, and we'll be very soon able to have again chances to, as it is necessary in our profession, to meet and work together, and not only online. On the other hand, as everybody did during the last 6, 7, 8 months, the Institute tried to react to these very peculiar times, and with all possible means try to adjust to the situation. One of these possibilities is just to try to find the best out of this difficult situation, and every once in a while have an occasion to get together and enjoy some nice conference, some nice talk, and being a community even in this peculiar way, being just online. Everybody's getting used to it. Before just giving way to mathematics and to the best part of this couple of days, I would like just to express my gratitude. And I do it also on the behalf of all of you, to the administrative staff of INdAM that made possible to adjust to this situation and to do all the work, the necessary work to readjust schedules, to keep our community together and trying to serve the community in the best possible ways, even in this special kind of situation that we have been in the last months. As you know, we made a large reschedule all our activities and try to make possible to anyway to keep the activities of the Institute alive. And this has not been a very easy task. And we believe that we made an effort to make possible a reasonable arrangements for next year. Most of our activities have been rescheduled and will be held according to the rules, of course. Hopefully, some of the activities will be held at least in a as now is common in mixed way, otherwise will be online. And we hope that anyway we'll be able to have chances to be together. A final, just before giving to give word to the speakers, just a final word. Of course, this special situation brought us the necessity of devising and inventing way to use the resources in a very efficient way. So I like to end my just these few words by announcing that we thought that the best way of reinvesting the resources was to think at the youngest part of our community, those who probably felt more the stress of this hard 2020. So very soon, before the end of the year, there will be a call for a substantial number of postdoctoral fellowships dedicated to the youngest part of our community, those who finished their PhD program in 2020 and those who are going to finish it at the beginning of next year. We thought that just to the best way to cope with this situation and to be optimistic was to dedicate our resources to the youngest, who are the real hope of our community. And with this, I think that I should stop boring you. And I like to introduce Professor Angela, before Gigliola appeared now, Gigliola Staffilani, who is going to be our first speaker. The chairman of the first talk is going to be Angela Pistoia, who will present our guests. And please, Angela, it's your turn.
Thank you very much, Giorgio. Okay, it is a pleasure and an honor for me to introduce Gigliola. I will make a short introduction because she is famous and she doesn't need to be introduced. But by the way, okay, Gigliola Staffilani studied at the University of Bologna, and after she earned the laurea, she moved to University of Chicago, where she studied dispersive partial differential equations with Carlos Koenig, and where she got a PhD in 1995. Okay, the PhD was followed by a postdoc at the Institute of Advanced Studies in Princeton, a tenure track at Stanford, where she became associate professor, and then by Harvard University, Brown University, and finally the Massachusetts Institute of Technology in Boston, where she became full professor in 2007 and where she still works. She is the first woman to become a full professor in pure mathematics at MIT. She works in harmonic analysis and partial differential equations. She has had a long-standing collaboration with the Fields Medal Terence Tao. They are both part of the celebrated I-Team, or the so-called Gang of Five, which also includes Colliandier, Keel, and Takaoka. Among the many awards she received are a Sloan Fellowship in 2002 and an AMS Fellowship in 2012. In addition, she has been a member of the American Academy of Arts and Sciences since 2014. Let me say that Gigliola is also actively involved in making the mathematical community more diverse by mentoring students from underrepresented groups. Finally, let me conclude this short introduction just saying that she is an extraordinary example for many young researchers and especially women researchers. Okay, so the introduction is concluded. This is a short introduction and it is a pleasure. Gina, maybe you should share the talk. Okay. So yes. Gigliola will speak about the Schrodinger equation as inspiration of beautiful mathematics. So please.
Thank you so much, Angela, for the introduction. It's even too long, I think. But before I start my talk, I just want to say that I was, in my time, long time ago, a recipient of a fellowship from INdAM. And that was the year between the end of my degree in Bologna and the beginning of PhD in Chicago. And in fact, when I finished my studies in Bologna, I had not really much of an intention to go abroad and receive and work towards a PhD in the United States. And it was at the INdAM when I met lots of young people that really benefited from this fellowship, that I learned about the possibilities going abroad and so on. So in my career, INdAM played a really huge role. Okay, so this is actually a pretty general talk because I wanted to explain lots of advances that happen in the general area of dispersive equations. And so maybe some of you already heard part of the talk. The second half of this talk is new and it presents some very recent results. So I like to try to begin the talk by showing a bunch of pictures. First of all, because it's always nice to have pictures in a talk, but also because it's kind of like a guessing game. And why are these pictures in this talk? And why are these pictures of completely different nature? So as you can see, some of them are actually real pictures, like a rainbow and the water and the rays and so on. And also the last one, which is a representation of Bose-Einstein condensate, but some of them are really mathematical, like the Perron tree and this ellipse that intersect the lattice of Z2 lattice. I hope that throughout the talk, I will make some connections among these pictures and also gives the idea that really when we study abstract mathematics, we put together a bunch of phenomena that at first glance do not have much in common. So to start, let me just say that the field in which I work since my original research when I was a graduate student with Carlos Koenig, in the last 25, 30 years has really taken quite a lot from different areas of mathematics. Of course, the first one, and maybe the one in the forefront, is harmonic and Fourier analysis. We all know that when we need to understand nonlinear phenomenon, well, we like to chop things up in smaller parts that are more easy to handle and then recombine everything. And this idea of recombining without adding too much extra stuff that we don't need and by still maintaining the essential message is the core of harmonic analysis, of reanalysis. And then I will show you how you can also use tools from analytic number theory and how analytic number theory now uses tools from harmonic analysis. There is this beautiful symbiosis between the two fields. And then, of course, math physics, we are talking about mathematics for physical phenomenon. And the tools that we use to analyze various questions in this general field of dispersive wave equations sometimes calls for the understanding of dynamics and from a very deep way. So dynamical system is part of that. And there are some branching out into symplectic geometry, which I will not show in this talk, and probability, which probably I will just touch upon. So since I'm going to have to tell a story, I'm going to have to introduce a main character. And to tell the story, I will use a very famous equations in physics. This is the Schrodinger equation. So we are all, people know about PDE here. So I will just briefly say that this part on the right-hand side is a linear part of the Schrodinger equation, which plays an important role, as you will see in a few slides along the line. And then in the right part, there is the nonlinear interaction, which here is a three-way nonlinear interactions. Of course, there are other phenomena that might have different kinds of nonlinearity, but let's stick to this. And I wanted to emphasize the constant in front. Basically, everything has been normalized, and this lambda, the importance of lambda more than how big it is at this stage, is whether it's plus or minus. Later on, this lambda will play a more important role, and I will get into that towards the end of the talk. Then we impose, this is an initial value problem, a Cauchy problem, so we have to impose an initial profile, and this is going to be the signal that, or the wave that we start with, and then we wanted to understand the nonlinear dynamics of it. Throughout the talk, my physical variable is going to be on the torus of dimension D. And this is not just a mathematical curiosity. It actually means that we are considering periodic solutions. It's very hard to study this kind of equations on general domains. And so I'm gonna, and you will see already in the, to get very sharp estimates already being on the torus, hence in the periodic setting, it's gonna be challenging. And since this equation describes physical phenomena, in fact, I'm going to go a little bit deeper into that in a second. There are some conservation laws that are inherited by this equation. And in general dimension D, there are two of them. One is the mass, which really corresponds to the L2 norm square of the solution U. And the other one is the Hamiltonian of energy that has a kinetic part, that's the gradient square, and a potential part, which reflects the nonlinearity. So this is the potential, this is an L4 norm to the fourth. The lambda plays a role because if it were negative, there would be a competition between kinetic and potential. And there are really, really important studies on the possibility of blow up in this case. Most of the studies have been done in RD, so on the usual Euclidean. Less has been done in the periodic case, but that's something that I will not address in this talk. So throughout the talk, my lambda is positive, which means that the combination of Hamiltonian and mass will give a uniform bound in time on the H1 norm of the solution. So since the conservation laws happen in a L2 based type of Sobolev space, most of the study of the existence, uniqueness, and stability of solutions of this problem is going to happen in the Sobolev space. And in particular, we would like to stay within the H1 norm and not above. And hence this, especially in higher dimension, is a very low regularity to do various estimates. And we're going to go back to that. Now, since we said that the Schrodinger equation is linked to very important physical phenomena, let me give you at least one link. So this is with the Bose-Einstein condensation. Now, the cartoon that you see in these slides is supposed to represent what the Bose-Einstein condensation is. So we're gonna, in the first top square, is a rectangle, you see the representation, very schematic representation of a gas made of bosons. And this gas is very diluted, meaning the distance between the particles is relatively large. And we wanted to understand what happens to this gas as we let the temperature goes to absolute zero, or in an equivalent, in a way, you can transform the problem into saying with specific conditions, what happens when the number of particles goes to infinity. So this is different than the usual way of representing interaction of particles via the dynamics of billiard balls. So we are going towards low temperature, and the best way to represent this phenomenon is by substituting the notion of particles with little wave packets. And you see that in the second cartoon. Now, if the temperature is relatively low, but not too low, then the distance between the wave packets and the wave numbers is going to be a different scale. But at some point, as you take t towards zero, there's going to be a critical critical temperature where the distance and the wavelength is going to be comparable, and interesting stuff start happening until at zero time, there is at zero temperature, zero temperature, there is the creation of this giant matter wave. And this is also the picture that was represented in the original slides where I put all those pictures. That will be the far left on the far down on the right. Okay, so now there has been an incredible amount of mathematics and physics, but rigorous mathematics in trying to understand this phenomenon. And obviously this is a limit situation, and you go from a microscopic, so a very small scale phenomenon, to understanding something that happens in a larger scale. And when you change scales in mathematics, it's very hard to capture the phenomenon itself. So let me tell you very briefly how this has been done, and not even that long ago. In fact, the resolution of this limit process in all mathematical glory happened relatively recent, into around 2005 and so on. And I will get back to the names of people that were involved in that in a second. So let me, just in these very quick slides, the representation of the wave packets and their interaction, of course, is given by a coupled family of equations, and this is the BBGKY hierarchy. And here there is a parameter n that you want to tend to infinity. N, let's say, is the number of particles, and there's going to be a large number, n number of equations that are coupled in a certain way, and this equation give the interaction of these wave packets. Now, what you want to do is to understand the limit as n goes to infinity. And that limit produce what we call now the Gross-Petaviesky hierarchy. And since you are going as in n goes to infinity, and then you go from this n number of equations to really an infinite number of coupled equations, all which actually are linear, but the interactions is what will be connected to the nonlinearity of the Schrodinger. So I'm not going to write neither the BBGKY or the Gross-Petaviesky for you, because I don't think it's informative this time. But let me just tell you how it's connected with the Schrodinger equation. So let's for a moment fix K. So the K is going to go to infinity, of course, and this it could be as large as you please in the Gross-Petaviesky hierarchy. But let's fix K, and then we fix what we call the physical space. So it's going to be given by vector xk, but each one of the entries in this large vector is a vector itself. In fact, x1 all the way to xk are positions in, let's say, RD, but let's go, if you want, think about 3D, that's a more physical one. And the Gross-Petaviesky is an evolutionary equation. There is a time variable, and you, again, can set it up in terms of initial value problem. So we're going to give an initial data. And this initial data I'm going to call gamma 0. And it's given in a product fashion. This is very, very common in physics. And it's the product of U0 at variable xj, and u0 bar, where bar means complex conjugate, at x prime j. And then you evolve this guy, and actually it's not hard to prove that one possible evolution of this initial data is this gamma k, which now depends on t, that is the product again of functions which now depend on t, and the relationship between u0 and u is that u is the solution of the Schrodinger equation with cubic nonlinearity with initial data u0. Now, proving that this gamma k actually solves the Gross-Petaviesky is not hard. You can just plug it in, just like we ask our students in our lower calculus classes to plug it in and check. And that you can do, and you see that formally at least, this u, the product of these u's, which give gamma, solves the Gross-Petaviesky. The question, which is really hard, is why is this the unique solution? So this was fully resolved, at least in dimension 3, by a series of wonderful papers of Erdős, Schlein, and Yao after serious work of Spohn. And the way I learned about this was really through a paper of Kleinerman Macedon that put the setting in the notation that was more familiar to me in the community of the dispersive equation. And then from there, I collaborated in a work with Kirkpatrick, Schlein, and myself that treated the periodic case. The original work of Erdős, Schlein, and Yao was in R3, and we looked at the periodic case. And then there is, as many of you might know, there is great work of Thomas Chen and Natasha Pavlovich at UT Austin, and Xuan Chen and Holmer when Xuan Chen was at Brown. Anyway, so this is now fully understood, but what I wanted to mention is something that I found interesting when I started working on this area, which is the following. So if you are in dimension 1, so you take the same equation, focusing or defocusing, doesn't matter what the lambda sign is, both on the line and on the circle, this is a very well-known example, integrable system. Now, many of you might know that the integrability of a system is a wonderful, beautiful, it has a lot of beautiful, wonderful properties that are very well studied in geometry, in algebra, and so on. But here, let me just remind you that one consequence of being integrable is like the existence of the lax pair or the existence of a theory of inverse scattering. And in particular, many people might know that they also imply infinitely many conservation laws. For the particular case of the Schrodinger equation, these conservation laws are made of a first higher order term that has the derivative order s, where s is an integer, and then lower order parts. So when I was thinking about this question with my student, former student, Dana Manderson, and talking with Andreana Mod and Natasha Pavlovich, we were wondering where does the integrable structure for the Schrodinger equation come from if we are thinking that the Schrodinger equation is very well connected with the Gross-Petaviesky hierarchy. So do we have anything in the Gross-Petaviesky hierarchy that at the when we connect with the Schrodinger equation, the obvious way that we know how to do, will also represent conservation laws? Or in other words, in an even more ambitious question is the Gross-Petaviesky hierarchy at dimension 1 an example of an integrable system? So we thought that this was actually some simple question, simple in the sense that we were expecting a lot of work to have done already in the literature, but actually not. And in fact, we proved that there are conserved quantities. Of course, when we talk about Gross-Petaviesky, we talk about operator instead of functions. So we have to clearly define what conserved quantities are, but we managed to prove that. But what we didn't do in that original work was showing all the other beautiful geometric and algebraic structure that an integrable system has. So we kept working on this, and we set up sort of a diagram, which you actually see here. This somehow comes from some of the interactions that us authors had that were asking the following question. So up on the top, and this sort of represents a little bit the first cartoon that I gave of the Bose-Einstein condensate, you have the many body system. So these are the particles that you interpreted as interaction of little wave packets that is described at the BBGKY. You take the n as goes to infinity, so you take the limit and you obtain the Gross-Petaviesky, just as I mentioned. And then down below you have the Schrodinger equation. The relationship is pretty clear between the two. Now, if we concentrate on the Schrodinger equation, there is an Hamiltonian structure, there is a canonical Poisson structure, and in R and tau in one dimension, in the cubical case, we also have this whole geometric integrable structure that was beautifully studied by, for example, Richard Palais. So our question was, what's up here in the many body system that's such that when you take the limit, you obtain this wonderful structure for the Schrodinger equation? And even what's up here at the level of the Gross-Petaviesky that is related to this great structure right here? So we set up to understand these questions, which actually we found were also asked by physicists about many years ago. And we formalized this question a little bit more clearly in the following way. So can the Gross-Petaviesky hierarchy be realized as an Hamiltonian equation of motion? So this was not known, meaning can you write the whole infinite system of Gross-Petaviesky as ddt of gamma equals this Hamiltonian vector field, which I'm going to call x relative to the Hamiltonian, which we don't know yet whether it exists, of gamma itself. Of course, in this setting, gamma is going to be an infinite dimension vector because there are infinitely many equations in the Gross-Petaviesky. And define, of course, what is the Hamiltonian for this Gross-Petaviesky is also the main goal. And what is the Poisson structure that you have to put in all this setting? So this was question number one. Then, can the Poisson structure, once we define, and the Hamiltonian, once we figure out what it is, can that be derived in a suitable manner from an analogous structure at the level of the BBGKY or at the level of the n particle system? So do we have a Hamiltonian equation and a Hamiltonian system such as dt gamma equals x now relative to the Hamiltonian of the n particle system of gamma itself, such that when we take the limit, we obtain the one for the Gross-Petaviesky? So this is another question. And then let's concentrate in dimension one, where we know that we have for just the Schrodinger equation integrable system. So does the cubic Gross-Petaviesky hierarchy possess an integrable structure? We already had proved that there were infinitely many conservation laws, but here we wanted to understand better the structure in the sense that there are infinitely many Hamiltonians or energy that Poisson commute. That's the part that we didn't know, with the Hamiltonian of the Gross-Petaviesky itself. And then the final question that we wanted to prove, so if we do find this conserved Hamiltonian that are in a good Poisson, that Poisson commute with each other, then we can, in fact, for each one of them, we can define an equation, which is a Hamiltonian equation, and are those related to the end Schrodinger equation that we already knew before, just like the Gross-Petaviesky is related to the Schrodinger equation itself. So these were the questions, and I have to say that after working pretty hard with the original authors plus Matt Rosenweg, who is a former student of Natasha Powell and now is my postdoc, we answered yes, which was expected on all these questions, but we had to set up a quite heavy machinery of notations in a sense to do that. And these are like, both papers are about 90 pages, so I'm going to summarize here very briefly. So for question 1 and 2, which was just about the Hamiltonian structure so on a dimension, any dimension, we answer yes, and our geometric constructions are based on what we call a quantized version of what some physicists already had put forward in some way of the, and these physicists, as I mentioned, they have been working on this in more of, as a physicist, and these were Marsden, Morrison, and Weinstein. For the question 3 and 4 that deal instead with the integrability structures, we like to say that what we proved is a quantized version of all the work of Richard Palais on the integrability structure of the Schrodinger equation. So we quantize what we mean with quantize. I'm not going to go into details because I don't think that this is the right setting to do that. Okay, now the good thing about this talk is that when I start going deep into something, I switch gear. So here we are. I'm going to switch gear now. And I want to go back to the original question of the Schrodinger equation and well-posedness, meaning existence of solution, uniqueness, and stability of the solution themselves. So, and I mentioned before that what we would like to do is answer all these questions of the well-posedness by remaining within the spaces in which the mass and the energy are defined, in particular then in the H1 Sobolev setting, or anything which scales like that. And clearly, if that's what we want to do, we have to interpret the equation in a much more weak sense than the classical one, since we cannot, or we don't want to take two derivatives. So we're going to recast this initial value problem into an integral equation, which we do by using Duhamel Principle. And you will see Duhamel Principle is going to be used over and over again in other parts of the results that I'm going to mention towards the end. So when we do this, we write the solution U in terms of the linear evolution. This is standard, plus the non-homogeneous term that takes care of the nonlinearity. Of course, this is just not an explicit description of the solution itself, because U depends on U cube. And here the linear part is just indicated with STU0. ST is the Schrodinger group, and it solves this equation here. And as I will write down a couple of slides, it's completely explicit, both in the Euclidean space and in the periodic setting that I'm considering here. But this new setup that you obtain via Duhamel is conducive to the use of various fixed point theorems, because once you define the right-hand side of this equality to be the operator, let's call it phi of u, then if you have a fixed point for phi of u, that will be your solution. As we know, these fixed point theorems also give to us uniqueness and give to us various property of continuity with respect to the initial data and so on. So let's say that now we are thinking about solving this question about existence and uniqueness via the fixed point. The main first step on this goal is to decide in which space of functions we're going to show that the right-hand side of this equation has a fixed point. For that, what we do is, well, at least if we have t small, we can think of this right-hand side, once we can handle it, as a small perturbation of the linear part. So let's concentrate on the linear part and do as many multilinear estimates as we can that will allow us to then control the multilinear, or in this part, cubic nonlinearity of the equation itself. So now we concentrate on the linear part. So these estimates, or multilinear estimates that I would like to do, are called Strickard's estimates. And here I'm just going to write for you the ones in the periodic case. And the type of a Strickard's estimate is LQ, space-time, YQ. Well, think, for example, about Q equals 4, which is what I'm going to concentrate on in a moment. That will allow us to estimate the 4-wave interactions, which is going to be good for our goal of proving a fixed point theorem. So now we are estimating this solution, which I'm going to write down below for you completely. And with what? Well, on the right-hand side, you want to put a space which is L2 based, because as I mentioned before, you would like to stay within finite mass and finite energy. The question is, for which Q, what kind of S do you have to put here when you have a whatever Q and whatever dimension? So let's take a special case, d equals 2. That's the first really interesting situation to look at q equals 4. And let's write down the solution completely. You do that by using Fourier Transform. So now you're going to have a Fourier series. These are the Fourier coefficient. You reconstruct with your basis. And here it's what the Schrodinger group does. It multiplies by I to the t. And then what you see here in parentheses is nothing else than the symbol of the Laplacian on your torus. Usually you might think that alpha 1 and alpha 2 are just 1. But we can think of them alpha 1 to be just positive numbers, and they depend on the possibility of having different periods in the two different directions that we are considering. And it actually makes a difference for the analysis whether the ratio of the periods is a rational number or is an irrational number. And we'll be talking about rational torus or irrational torus. Okay, so the person that actually had the confidence of start looking at these questions first was Bourgain. And why was that a hard question? In fact, if we were thinking at equivalent Strickard's estimates in R2, they had already been proved. In fact, the family of Strickard's estimates is much larger. So why was it hard to do in the periodic case? The reason why it was hard is because the basic proof of Strickard's estimates in Rn is based on the so-called Fourier restriction theorems, and they themselves are also based on oscillatory integrals and being able to estimate oscillatory integral by using integration by parts. So when you have, instead of an integral here, you have a sum, you cannot do integration by parts. And so people were kind of paralyzed by it and took the courage of Bourgain to start looking at it, especially because he knew number theory, and you will see where that comes in. Okay, so the estimate says in dimension 2 that the L4 norm is bounded by the initial data in H epsilon. You need a positive derivative to do the estimates. And just for comparison, in R2, you can put here L2 norm, which is the mass itself. So what he proved was exactly that. One remark that I want to make is that in the estimate that I wrote here, I truncated the time, which is something expected since the dispersion doesn't really work in a periodic setting. It's meaning that the size of the amplitude of the solution doesn't go to 0 in time, so you have to cut off. But here he put the circle. Why is that? It's because he considered the rational case. So for example, think of the situation in which the two periods are the same, or the ratio is a rational number. In this case, these two numbers, alpha 1 and alpha 2, which in general you can pick to be just positive, in his case were actually natural numbers. And hence, if you think of alpha 1 and alpha 2 to be natural numbers, and n1 and n2 are already natural numbers, then you can, or they are in Z2, then you can see how this part, which involves time, is also a periodic function. But if alpha 1 and alpha 2 are just positive, this is not true. It's not a periodic function, hence you have to cut the time in a certain interval. But in this case, he put here the torus itself. Okay, so he proved it, and there is one, and actually the proof is not very hard. He used Plancharel, he used like writing Fourier transform of product as a convolution, but doing some Holder inequality and measuring a certain set of lattice points. So the set that he has to measure is exactly this. So the n and Z2 such that this relationship is true, where R, alpha 1 and alpha 2 are actually natural number. This is the constraint you have when you look at rational tori. So this is this estimate is actually done sharply by Gauss' lemma, and it is in fact an information that comes from analytic number theory. So the exact estimates is done with respect to R. So in other words, R is basically the radius of this ellipse. And it's log R, log R, which is much smaller than R to the epsilon. That's where the loss derivative comes from. So now we looked at the rational torus. What about the irrational torus, or any torus for that matter? Well, it took about 20 years for this to be resolved, again by Bourgain and Demeter. And so now we have the full estimate with the same exact loss of a little derivative. But now, of course, we had to truncate the interval 0, 1 because in general, this solution in T is not periodic. And surprisingly enough, there was no analytic number theory involved to prove this estimate when Bourgain and Demeter worked on it. In fact, it is a corollary of a much deeper theorem called L2 decoupling theorem, which goes back to restriction of the Fourier transform on surfaces with curvature. And I'm not going to go into details, but it really is related to problems such as the Kakeya problem, which has seen big stars from Bourgain to Tau to Wolf and so on, working on it. Okay, now one remark that I wanted to make at this point is that actually just the Strickers estimate, the way I set them up, are not enough to prove the full well-posedness. So there was something a little bit more sharp that needs to be done. This is improved bilinear estimate that I did with some of my graduate students and postdoc. And then an very interesting result is that Deng, Germain, and Guth proved that if you are actually irrational, then the length of time in which the Strickers estimate hold is longer than if you were rational, which makes sense if you think about the wave hitting the boundary in a rational torus, as it will come back to itself much more often and will increase the nonlinear setting of the problem, and hence maybe the estimates need to be done in a smaller interval time. And a really cool result is that the techniques used to prove the L2 decoupling were implemented I wrote here sharp decoupling for curves, but the point is that this gives the solution of a very important conjecture in analytic number theory, which is called the Vinogradov mean value theorem, which consists in estimating the number of solutions of certain systems of Diophantine equations. And so this was done by Bourgain, Demeter, and Guth. So at this point, it looks like these techniques of harmonic analysis, of restriction of Fourier transform, and so on, now are informing theorems in analytic number theory. Okay, so now it's time to switch again, and I'm gonna go back to our main character of the talk, which is the Schrodinger equation. And at this point, we have in our, at our use, the Strickers estimate, we can do the fixed point theorem, and hence we can get the local well-posens in HS. We are in dimension 2 here. Of course, there is equivalent Sobolev space if you are another dimension, but in dimension 2, both periodic, rational, and irrational, we have a local well-posed when you just have to add a little bit of derivative, so s greater than 0. But in the case in which we are defocusing, meaning lambda equals 1, we have the whole Hamiltonian that bounds the H1 norm. So by iterating the local well-posedness and using the conservation of the Hamiltonian, you obtain global well-posed for s greater or equal than 1. There are results for s slightly less, s little bit less than 1 with almost conservation laws, not important for the rest of our talk. So now the main question is becoming, what happens to the solution at later times? So at t goes to infinity. Is there anything special that we can say about the solution, its behavior, and so on? I will mention in a moment that if instead of the periodic setting, you are on R2, then there is the so-called scattering, which means that as t goes to infinity, both positive and negative, this reversible equation, you approximate or you get close to a linear solution. So your dynamics become very simple, much simple, is in fact the dynamics of the linear problem. But in the periodic case, this is not expected, hence scattering is not expected. So what can we say about this solution? So one of the questions you wanted to answer is on transfer of energy. So let me try to explain with a picture what this means. So we are in the periodic setting. We are giving an initial signal at the beginning. So that's t equals 0. And I'm representing here the Fourier coefficient square. And what we ask is whether as t evolves, this bump, which is close to origin, means it's all concentrated for very small frequencies, is going to move to very high frequencies. Now, if there is such a movement, which is actually goes, and I'm going to talk more about this is in the realm weak turbulence, forward cascade, and so on. If there is such a movement from low to high, this cannot happen in a very disordered way, meaning the problem is rigid in the sense that, for example, if you look at the area of the subgraph by Plancherel, that's basically the mass, hence it's conserved. So the area of this subgraph has to be the same no matter which time you're looking at. So there is this constraint. Of course, there is also the constraint of the Hamiltonian, which it's not as easy to see in this picture, but there are constraints. So this motion from low to high, if it happens, it's very rigid. Another question that you can ask is, if there is such a migration, how is it going to happen? So I put the two little pictures here. So in the first picture, it's much more disorganized. It goes down and then it goes up again, but overall it goes down. While in the second picture, it goes down in a much more direct way. So we don't know anything, as far as I know, in question number 2. We know a little bit about question number 1, and I wanted to concentrate on that. So let's concentrate on question number 1, just the general idea whether there is motion from low to high. So there are 2 different approaches for this. So the approach number 1 is the following. We're going to look at this expression. So what we are interested in understanding is where this part, this piece here, it grows as t goes to infinity when and it's concentrated in high frequency. So to understand this concentration towards high frequency, we're going to hit with this weight. And so this amount, in particular, when you sum for all the frequency, should get bigger. So it should grow if there is a migration to higher frequency. But then you recognize that this is nothing else than the HS norm square. So what we study is the limit as t goes to infinity, and you can do this at minus infinity equally, of this HS norm. Now, from the PD point of view, PD approach, Bourgain, Cookson, myself, my former student Soinger, Deng and Germain, and here the mentioned I team, Carl and Fau, myself with my postdoc Wilson, and Hani, Pusadera, Tseko, Vishilia, and so on, had some partial results on this. From the computational approach, really numerical approach, I know some work by Yulin Pan. And then there is a really beautiful work on dynamical system approach with House and Procesi, Kaloshin Guardia, Bert and Masper, on more recent papers on that. And I'm gonna suggest a little bit about the first approach, and then I'm gonna go to the second one. The second one is based on finding an effective dynamics. So one approximate the equation at hand in various ways, maybe by a box and then taking the limit of the box, or maybe by discretizing, making a discrete system and then take the limit of the mesh. So whatever way you want to do, then you take limits to get an effective equation. And I'm going to talk a little bit more in details on this. And this is really the realm of wave turbulence theory. Fundamental original work on this idea of taking limits is that Perls, Hesselman, Nazarenko, Newell, Zakharov in alphabetical order here. And in many works, this taking limit is not mathematically rigorous. And a lot of the recent attention on this has been devoted in making these limits rigorous. So let me start talking about the first approach first. Okay. So the first approach was that about the growth of Sobolev norms. Let me recall a few facts that should center the problem a little bit better. So fact number 1 is that complete integrability, which I already mentioned, might prevent its growth. In fact, I mentioned before the situation 1D qubit, but there is also the KDV. So the infinite many conservation laws give you a control in this on any of the HS norm if S is a natural number. So the HS norm do not grow both in the periodic and non-periodic. The scattering, which is something that I also mentioned, that here I'm going to write more precisely, also prevents growth of the Sobolev norms. So for example, look at the defocus in cubic and LS in R2. And if U is a solution in HS, any S you want, then there is a function U plus in HS such that the linear evolution that U plus approximate U in the HS norm as t goes to plus infinity. You have the equivalent result minus infinity. These are actually a recent result of Dodson. And as a consequence, if at infinity the solution becomes linear basically, and the Schrodinger group is actually a unitary operator in HS, then immediately via a triangular inequality, you get the UT is uniformly bounded. So there is no growth in R2. If you want to see any growth, you have to be in the periodic case. So then if you are in the periodic case, well, there are two questions you can ask. How much of growth can you expect? And can you exhibit a solution that actually grows? So the first question, we call it bound from above. And this is work of Bourgain and also my former student Schrodinger. And at least in the case of the cubic two-dimension, any torus now, you have that HS cannot be, the HS norm cannot be bigger, they cannot grow bigger than the polynomial of this degree, basically 2s. But this is not what people expect. People expect at most it's called logarithmic type, which is in fact the case when you have the linear with potential. But that's where we are now. It would be great to have a much better handle on this. Then the bound from below, which is the other question, is do we have solutions that actually grow? Well, this is not clear either. And I'm gonna remind you of two facts, two results here. The first one is with the I team that reads in the following: fixed order of derivatives, not important, large if you want, and a small quantity delta and a large quantity k. Then if we are in a rational torus, I can prove, this is a very important, it's rational here, I'll tell you in a moment why. I can construct for you an initial data U0 in HS, such that when you measure it in the HS norm is very small, as small as you please, but if you wait a long time, it's as big as you like. Of course, you have to fix delta and k first, and then you get the result. There is a sort of companion result, again, the rational case, proved by Carl and Fau, and in their case, instead of controlling the HS norm, what they construct is actually a solution itself, and what they control is the size of the Fourier coefficient. Okay, so just something about the proof of the fact 3. Is this actually a dynamical system? What we do is we go from an infinite dimension system of the Fourier coefficients, if you like, for the full equation into a toy model, which actually approximates the full equation very well. It maintains also the various conservation law. And for example, the conservation of the L2 norm tells us that the whole dynamic of this toy model happens on this pink complex sphere, if you like. There are obstacles to go from low frequency to high frequencies because there are these great circles which are invariant. So you want to avoid them, otherwise you don't go anywhere. And what you want to prove really is that if you start close to the first great circle, that will be lower frequency, you can avoid all the other ones and end up in the last one, that's the high frequency. And this, in fact, can be done. There is some elaborate analysis you got to do, but that's really the meat of the result is exactly that. We didn't have in our paper any good control how long it will take. That T was incredibly huge, but then people who know how to do dynamical system better, like Guardia and Kalosh and House and Procese, they had a better control on how long this will take. Now this ends the first approach that I want to make a remark. I mentioned a few times that these two theorems that the one of the I-team and the one on Carl and Fau were proved for rational tori. What about when the torus is irrational? Well, with Bobby Wilson, we proved that there is something different that happens, and both constructions, both those previous results construct the solution cannot happen. The constructions cannot happen. We are not saying that there is no growth. We just say the constructions that were used in those two theorems to resolve do not work. And so this doesn't mean that it's not transfer of energy, although some numerical analysis of Julian Pan shows that actually might be really different in the irrational case. Now I want to spend a little bit of words, and this will conclude my talk, and a few more slides, but this is about approach 2. So let me start with the setup. So we start with U, which is the solution of some dispersive equation. Think of it as Schrodinger, KdV, generalized KdV. KdV is conservative, so you don't want to use that, but a dispersive equation. And let's concentrate on the Fourier coefficient. And now I'm going to give a name to it. That's AKT. We start with a sequence of these Fourier coefficients. And here we use a little bit of probability. And in fact, we think of them as independent random variable. I'm not going to do the whole probabilistic setup, just think of them as independent random variable. And then we define NKT, the expectation of the size of my Fourier coefficient. If you remember, the size of the Fourier coefficient square was exactly what I represented in the first cartoon when I mentioned the idea of transfer from low to high. Then there is when I first introduced approach 2, it said that you take the equation and then you do various kind of approximation. Large box limit, weak nonlinearity limit, both these limits together. What does it mean, weak nonlinearity? Well, it means that that lambda, which is in front of the nonlinearity, which before I said to be just plus or minus 1, in this setting, that lambda goes actually to 0. So that's what it means, weak nonlinearity. And what you want to do is obtain from these limits that you would like to make rigorous an equation for NKT. And actually this equation has a name, is the Kolmogorov-Zakoro equation. And we do have these equations because physicists have taken these limits somehow, not in a rigorous mathematical sense. So the equation is there. What is not quite there yet is this taking the limit in the right way. Okay. So let me mention, and maybe many of you already seen this paper, but there is really a great series of papers that have appeared recently, which goal is to, with given certain condition, make this limit process rigorous. And I'm going to distinguish them into two classes. The first one is where the work Lockerin and Spohn behave. And in their result, we said that the type of probability measure that they use, I'm not being very precise here because I'm not telling you much in detail what that means, but the probability measure that they use is the Gibbs measure, which is an invariant measure. So that's a statistical equilibrium approach. The second group of result is Bafau, Bakmasa, Germain, Hani, Chatin, and Dengeani, and Collot-Germain. These are very recent. This is out of statistical equilibrium. The probability measure that they use for the initial data to start with is mostly Gaussian, and that's not an equilibrium measure, and so it's of different nature. Now, a very, very recent result, and this is with my collaborator, Bin Tran. In particular, I will say that Bin is totally the driving force of this. We consider a specific equation for, in this particular case, is, I would like to call it a generalization of the KdV equation. And the way it is written, you see the Laplacian here, but then there is an extra derivative with respect to the first coordinate. So this is a cubic derivative. Then the lambda here is what makes a weak nonlinearity. The nonlinearity is the typical one of the of the KdV. So you have a derivative again in the first direction of a quadratic of phi square. And then we add some noise with again a coefficient in front, which will go to 0 as lambda go to 0. And in this notation, notation here means there is a mix of convolution Stoyanovich product. And of course, we give the initial data. We are telling you here how big the CR is, and so on. So this problem was actually inspired by a recent work of Au. And we are in the assumption, one assumption that we make here is actually that the noise is small. And that's an important one. Okay, so let me write the statement of this result. Again, let's think of the Fourier coefficient of my solution. I'm going to use the same notation, that AKT, and consider the 2-point correlation function. So basically, this is the average of your coefficient square with respect to a certain density function. And in our approach, again, most of the emphasis is on this density function rho. It's not on the solution itself, but it is on solving the equation for the density function. But the main theorem says the following: assume that we are in the periodic case, but we need to be dimension greater or equal to 4. It's important to be in higher dimension for the argument to work. And under suitable assumption on the initial density function rho, if t is of order lambda to the -2, and this is really important because lambda to the -2 is the kinetic scaling, and the previous result that I mentioned by Fau and Deng and Ani and Buckmaster and all, and Collot and Germain, they do not reach the kinetic time scaling. So this is, as far as we know, is the first time out of equilibrium which kinetic scaling is reached. And what we prove is we make strong and precise and rigorous this limit as the weak nonlinearity goes to 0, so lambda goes to 0. And in this case, the way we approximate the equation is by doing a discretization. So there is a mesh, and so that parameter goes to infinity. So this density, sorry, this 2-point correlation function has a limit, and this limit satisfies, in fact, rigorously the 3-wave kinetic equation. So I'm not gonna say more because I went a little bit maybe over time, but the details of this proof is are pretty intense. And let me just mention a little bit what is what's the approach in general. So we employ a framework that is built on top of that Erdős, Salmhofer and Yau, and Lucarin and Spon. So this approach implies the use of deep use of Feynman diagrams and some stopping rules. So it's not important exactly what it means, but for this diagram, you have to decide when you stop doing that. And that number, as lambda goes to 0, goes to infinity. So you need to have something that controls that growth. And that is a power lambda to the θ1. And then you have to understand when this θ1 is getting bigger or small. So I'm not sure if I have any more time. So maybe my chairperson can tell me.
Yeah, so you have at least 10 minutes.
Over, or I have more 10 minutes?
No.
Oh, great. Okay, good. No, thank you.
At least 7 minutes, so maybe 10
minutes. Oh, perfect. Fantastic. Okay, so I don't need to rush. So let me just go a little bit slower. Okay, so for each of these Feynman graphs, we wanted to have a control of the situation. So let me mention that where does the Feynman diagrams come from? Again, this comes from using the Duhamel approach and an iteration. So you start with the linear solution, and then you put inside the non-homogeneous part of the Duhamel your linear solution, and you keep repeating and putting inside that. And there is a schematic way of writing that analytically, and the same thing with graphs. These are the Feynman graphs. And then, of course, you have to control each one of them. And there is a whole, actually beautiful description of how to integrate on this Feynman graph in some lecture notes of Erdős. That's actually where I learned this. And in doing this integration in the right way, you start obtaining coefficients lambda in front of it. Remember, lambda goes to 0, that controls these Feynman diagrams. Now, when we have these Feynman diagrams, we're gonna, in our work, we're gonna separate into two families. There are the Feynman graphs or Feynman diagrams that are pairing, and the ones that are non-pairing, whatever that might mean. You know, we're gonna post the paper in a month or so, so hopefully people who want to learn about this can go there and look. But the important thing to note is that in these two classes, the non-pairing ones, actually, when you do the integration over them, are such that it gains lambda to the θ1, where θ1 is large enough so that when you take the limit in there, you get 0. So they will not account for anything. So, but then we need to proceed and analyze much more in details the graphs that are so-called pairing. And in doing that, we used quite a lot of result from graph theory. And it turned out that some of them were close enough to what we needed, but not quite there. So we really had to reprove some theorems in graph theory that are based on work of Estrada, if anybody knows that. And in the refined classification of the so-called, on these parts which are non-pairing, we have a specific class of it. So we call them the ladder graphs, and they do not give 0 contribution. In fact, they are the essential ones that will give us the pieces of the 3-wave kinetic equation. So the one thing that I want to remark here is that in our case versus the situations that, for example, Lucarin and Spohn or Erdős and Yao use, we have a quadratic nonlinearity. In our equation, which is a KdV type, there is a derivative in the first coordinate of the square, while in the Schrodinger equation that Lucarin and Spohn use, there is a cubic nonlinearity. So in our case, the nonlinearity hence is quadratic and makes the study of the Feynman diagrams much harder. And in fact, our analysis for this reason is much more complex than the one of Lucarin and Spohn. And I'm going to finish here and maybe ask questions if you want. Thank you.
Thank you, Gigliola, for your wonderful talk. Okay, let me see if there are any questions. I'm looking at the chat. Okay, if somebody in the room has some questions, please feel free to. Okay, Marco?
Yeah.
Okay, please.
So I was wondering, I'm not an expert on the nonlinear Schrodinger equation, but I was wondering if, particularly concerning the asymptotic time problem, if we add some kind of dissipation, for example, if we consider the complex Ginzburg-Landau equation, if the natural result, I guess, are completely different or not?
Yes, my understanding is different. And in fact, it's very interesting what you mentioned, because there are situations in which you do have to add some dissipation with a small epsilon in front to claim that there is a solution, and then let the epsilon go to 0 and maintain the features of the dispersive equation though. So you don't want to use anything, any estimate that comes from the dissipation that does not transmit later on to the dispersion. So in particular, I'm mentioning the work of Koenig, Pons, and Vega, who proved well-posons for really for Schrodinger systems that have some gradient or derivatives and nonlinearity and so on. In that work, they had to add dissipation, epsilon, in fact, in that case, I think it was Laplacian of order 4 or something like that, to prove that there was the solution for the system with that, and then they let epsilon go to 0, but they couldn't use any of the property that you might have that are specific for a system that has dissipation. But since you mentioned, I didn't give the details, but in this recent work that we did, and I was talking about the density function rho, which tells you how these coefficients get distributed later on in time, the Fourier coefficient get distributed. For the density function rho, the presence of the noise corresponds, in fact, in having a piece which is a dissipation. So for the equation of the distribution function rho, we do have a gain. If we put the noise in there, that equation will have a dissipation type effect. If we remove the noise, it becomes a transport equation, which is a completely different beast to treat. So in a very indirect way, we are using, thanks to the noise, results that comes from having a much more favorable situation. But this is only for the, not for the function, for the solution itself, but for the density function rho.
Okay. Giuliana, let me look at the chat. There is a question. Okay, I'm reading. Interesting talk, thanks. This is Gianmaria Dallara who wrote. Concerning Fact 3 on low to high frequency transfer, is there any solution starting with a small HS norm and was H norm blows up no matter how slow the rate known? Is any solution starting with small? Did you understand?
Yes, so I think it's any solution known that starts small, but then it grows to infinity.
Exactly.
No, that's the interesting point is that, for example, in this construction that we did, we don't know what happens after capital T. So at the beginning, we thought maybe we can patch together a bunch of this solution that we construct and make them grow together, so that then we can continue this growth later on in time. But there is an obstruction to do that, because like I said, the problem is very rigid. So no, we don't even know whether after this time T, you go back to being small again. The result of FAU is slightly different. FAU, Carl and FAU, they do not talk about the HS norm though. They just talk about the explicit Fourier coefficient, and they say that anywhere later on in time, there is a reminiscent of something that comes from time 0, but not the growth. On the other hand, I have to say that there is the work that I mentioned. Let me, let's see if I can go back to, yes, the work of Hani, Posader, Tsetko, and Vishilya, they do in fact produce a solution that grows in time, but the equation is not purely on the torus, it's in a mixed manifold that has torus cross R to some dimension, which now I don't remember. So in that case, there is growth.
Okay, there is a second question by Gianmaria Dallara. He asked if is it easier if one allows the initial norm to be large?
I don't think it's easier because these problems, they have a scaling, at least the equation I'm looking at. So I said small because I wanted to emphasize that you can start with something small and still grow, but you can rescale and make it and reshape the problem in this way just by doing scaling. In fact, in the proof, that the original proof that we have, which is that deals with here, with this dynamical system thing, the original proof, I mean, we start by proving that we have initial data of size 1, if you want. And then the way we say that you can actually make it as small as you want, it's by doing the scaling in an inverse way. So yeah, I think it can be rescaled and it will not make things easier.
Okay. Giulia, let me check if there are any other questions. No, not question in the chat. And in the room? Okay. If not, we thank you again for your nice talk. And we will resume at 4:45 with the second speaker of our Giornata INdAM, Miers da Fermos. So thank you, Gigliola.
Thank you so much, Angela. Thank you, everybody, for listening to the talk. Thanks.
Bye.
Thank you.
Bye.
Ora sono le 16:45, penso che possiamo ricominciare. Quindi è un grande piacere per me poter introdurre il professor Mihalis Dafermos, il professore he's a professor at Princeton University, so sorry for beginning in Italian. He's a professor at Princeton University starting from 2013. He also held the chair, a loading chair of astronomy and geometry at the University of Cambridge, starting from 2015. His research earned him several awards and honors. Besides being a fellow of the American Mathematical Society, he got the Adams Prize and the Whitehead Prize. He got his PhD in 2001 I think, at Princeton University. His advisor was Christodoulou, and his main scientific interests are PDEs, particular PDEs arising from general relativity and gravitation. He got many astonishing results, among which I would like to mention. He started from, there is the famous result of incompleteness result of Roger Penrose, which recently got the Nobel Prize, and together with the Igor Rodiansky, he got information on the structural singularity that was predicted by Roger Penrose. Moreover, he gave a rigorous mathematical foundation on the inflation scenario of Werner Israel and Poisson, and he get an important, starting from his PhD, he got the important result concerning the stability of the black holes, in particular of the Schwarzschild geometry. So his work is one of those examples in which rigorous mathematical methods are crucial in understanding physical theories. And so today we will talk about the stability problem for the black holes. So please, Mihalis, go ahead with you can share your screen, I think.
Okay, let me try to share my screen.
Go ahead. Thanks.
Yeah, just 1 second. So do you see indeed my screen?
Yes, it's fine.
Okay, thank you very much. So thank you very much for that introduction. Again, as Giuliola said in her talk, I think it was a bit too long, but thank you very much. And it's a big pleasure to give this talk. I certainly would have preferred to have actually been in Italy, but this is the situation, and we will indeed try to make the best of it. So the title of my talk is The Black Hole Stability Problem in General Relativity, and this is really the question of what happens when you kick a black hole ever so slightly. So let me give you a little plan of what I hope to tell you. So I'll begin with a crash course on general relativity for mathematicians. This will be the shortest course in general relativity you've ever taken, but hopefully it will be enough to understand the rest of the talk, and in particular to understand what a black hole is. So the next thing that I'll discuss is what a black hole is from the example of the first black hole solution to be found, the so-called Schwarzschild solution. And then I'll present what will be in some sense the main result that I'll talk more about in this talk, namely a nonlinear stability of Schwarzschild. So this is a joint work which is forthcoming with Taylor, Holzhegel, and Rodniansky, and I'll discuss that later. And then I'll discuss the full black hole stability problem, and finally the case of non-zero cosmological constant, which I'll explain what that means. Okay, so off we go. let me begin with this crash course on general relativity for mathematicians. So the place to start is with Minkowski and his geometric reinterpretation of special relativity. So what Minkowski understood, and here you see a little excerpt from his original paper from 1908, is that the principle that the speed of light is a universal limit for all propagation can be re-expressed as the statement that the following red cone in space-time, which is determined by this equation here, where c is the speed of light, is objective. Okay? So instead of thinking of space and time and various coordinate systems, think of space-time, so add the sort of t dimension to space, and then think of these cones in space-time. They are objective. Okay. They have, that's to say, meaning independent of coordinates. So we will see later in the talk many cones, so it's important to get accustomed to these light cones early on. All right, so in particular, to visualize Minkowski space, as it's called, you should think that at every point there is a cone. Okay, and now instead of thinking of our coordinate axes t, x, and y, let's forget about them. That's not actually what's important. What has physical relevance is the notion of proper time. So it is this line element, c squared dt squared minus dx squared minus dy squared minus dz squared, which was first introduced by Minkowski. And what is the physical interpretation of this? Well, it's very simple. If you have a world line, so a world line is an allowed trajectory in space-time of a physical object. Okay? And the principle of relativity, by the way, is that to be an allowed trajectory, this will be important later on, so it's good that I say it early, okay? The tangent vector of the curve should be everywhere inside the cone. Okay? So as I've drawn it here. So if you have an allowed trajectory or a world line in space-time, then proper time felt by the sort of this particle is simply the integral over that curve of the square root of this expression. Okay, so that is proper time, and this is something which is directly measurable. And the amazing thing is that this notion of proper time, secretly, it also includes Euclidean geometry. Right? So in particular, you can reconstruct Euclidean geometry and the Euclidean metric on constant t slices from this physical notion of proper time. So time and geometry sort of were united in the context of Minkowski spacetime. Okay, so in particular, you can consider observers which locally maximize proper time. And so this maximization is sort of funny. Why not minimize? Well, this has to do with the funny signs in this line element. And these turn out to be precisely what characterizes inertial observers. Okay. So inertial observers are precisely those world lines that maximize locally proper time. And well, not surprisingly, in this geometry, these turn out to be straight lines in Minkowski space. Okay, straight lines whose tangent vector is everywhere inside these cones. Okay, and this is precisely what gives rise to the celebrated twin paradox, which, okay, if you know what that is, you can read it off this picture here. Okay, so this is Minkowski space. So where does general relativity start? Well, general relativity starts with the attempt to incorporate the force of gravity into relativity. And whereas sort of Einstein originally attempted to find a theory of gravity which was compatible with sort of special relativity as it had been formulated before, he realized that that was not possible. And he made this very inspired leap with the help of his collaborator, Marcel Grossman, that in order to incorporate gravity, you had to replace Minkowski spacetime with a curved spacetime. That's to say, the right way to incorporate gravity was to make the metric element depend on the spacetime position. Okay. So in modern language, what this means is we replace sort of the Minkowski metric with a general Lorentzian metric. And the Lorentzian metric is to the Minkowski metric exactly what Riemannian metrics are to Euclidean metrics. So in even more modern language, the insight was to replace flat Minkowski space with a general curved Lorentzian manifold M4, G, okay, where G is a metric. This is what it means to be Lorentzian, with signature minus plus plus, which is exactly the signature of this metric, except I've reversed the sign, as is conventional, at least on the East Coast of the United States. All right, so this is how one tries to incorporate gravity. So what does it mean that this incorporates gravity? Well, one can describe in this formalism the trajectories of freely falling observers in a fixed gravitational field. And the postulate is that freely falling observers in a fixed gravitational field governed by this metric G, they just correspond to curves which locally maximize proper time. Okay, that's to say, again, such that this relation obtains. And of course, this is nothing other than geodesics in the space-time M, G. Okay? So freely falling observers are, in some sense, what the exact relation of inertial observers in special relativity. Okay. So with this very, very nice insight, Einstein was able to incorporate in principle gravity. But of course, to come up with a theory of gravity, it is not sufficient to say what would happen to freely falling observers in a fixed gravitational field. You also need an equation for the gravitational field. Just like in Newtonian gravity, it is not enough to say that we have a theory that if you have a given gravitational field, you know how massive point particles move. You also have to know how the massive particles generate the gravitational field. So this is something that Einstein struggled with more, finding an equation for the geometry of spacetime. And finally, in 1915, he got it in this celebrated paper that you see here. So here is some German from the paper. I don't know German, so let's get rid of it. And so here you see the celebrated Einstein equations, which govern the geometry of your spacetime. So what is this equation saying? What is this an equation for? So equations have a left-hand side and a right-hand side. And let me first tell you what the right-hand side is. So the right-hand side of this equation has something to do with the matter content of space-time. So you really should think of this as the general relativistic analog of the Poisson equation for Newtonian gravity. That's to say, it's the general relativistic analog of the equation Laplace phi equals 4 pi me, mass density. So the right-hand side is really the analog of mass density. So it's the matter content of your spacetime. And the left-hand side, this what's here written as capital G I me, is part of the curvature. So it's part of the curvature. Okay, so it's part of the curvature of G. So the equation says that part of the curvature of G is related to the matter content of space-time. So very often, it's traditional, we like apples in gravity, so it's traditional to illustrate this by the following picture, where you have this apple corresponding to matter, and the matter is curving somehow the space-time. So let me make two remarks at this point. So remark one is especially pertinent since I'm giving this talk in Italy. So it turns out that what is this thing on the left-hand side was secretly the so-called Ricci curvature tensor of G. So the Ricci curvature was actually something unknown to Einstein, which had been introduced earlier by Ricci Kurbastro. So as a result of that, if you notice, I just pulled the first one on you, in Einstein's paper, this was denoted by G, but actually it's now traditional to denote this by R. So this is sort of the form that one would have seen the equation in Einstein's paper had he been using this notation. So this is actually a warning. This is a deep fake. Okay, so this this equation here does not actually appear in Einstein's paper, but he fortunately was using RIM for something else, and I was able to move it. So that's one comment. And actually now we typically use the notation G I me for something else. Okay, so anyway, that's one historical comment. But the other more contentful comment is the following. It turns out the Einstein equations are non-trivial even in vacuum. That's to say, even in the absence of there being any matter in your space-time. So we can get rid of the apple, that's to say, and one still has non-trivial solutions. One has non-trivial global solutions, in fact, where there's no matter in the space-time anywhere. So to paraphrase my academic grandfather, Johnny Wheeler, what's going on here is that space itself is telling space how to curve. This is really related to the fact that these equations, as opposed to the Poisson equation of Newtonian gravity, these equations are nonlinear. This is very fortunate for the purpose of this talk, because you will never see any more matter in this talk. Believe me, the world would be a lot better if there was no matter present. Okay, so even in the absence of matter, the equations are non-trivial. And in fact, in the vacuum, curvature propagates as a wave. This was something already noticed by Einstein. So curvature propagates away as a wave. And now, of course, as is very well known to most of you, such waves have been directly detected on Earth by LIGO and Virgo. Okay. So secretly, the fact that curvature propagates in vacuum as a wave is telling us that the equations are hyperbolic. So this equation is secretly hyperbolic. And this is a very fundamental fact, because it suggests that the correct problem to pose for the Einstein equations is the initial value problem. And so this is the last part of the crash course, the last element that will be important for us to go further, is that indeed the Einstein equations admit a well-posed initial value problem, as you would expect of a system of hyperbolic equations. And this is the celebrated work from 1952 of Yvonne Choquet-Bras, then known as Fourier. And so her theorem is that given an appropriate notion of initial data, and I'm not going to make that more precise here, there exists a unique solution of the Einstein vacuum equations, at least for sufficiently short time. And so, as sort of revolutionary as this theory may be, it's very much in the spirit of classical physics, in that there's a well-posed initial value problem. And so in particular, if you have some explicit solution, you can study dynamics, you can study dynamical questions like stability. Okay? So when we later on in the talk go back to the stability question, we should always remember that the reason we can ask such questions is because of this theorem of Yvonne Choquet-Bras. Okay, so this is really the crash course. So let me just give a summary. So general relativity is described by a Lorentzian manifold M4 with a Lorentzian metric G, and physical observers correspond to world lines that always stay inside the null cones. And in fact, freely falling observers correspond to geodesics, which again always stay inside the light cones. Okay. The equation governing the theory, at least in the absence of matter, is the Einstein vacuum equations, which are just the statement that the Ricci curvature of the space-time vanish. And these equations have non-trivial solutions. In fact, they have a non-trivial initial value problem. So you can build solutions, principle, by solving the initial value problem for appropriate initial data. And this is precisely the theorem of Yvonne Choquet. Okay, so with all that said, let me continue to the next topic, which is the Schwarzschild black hole. So the Schwarzschild solution is the first non-trivial solution of the Einstein vacuum equations to be discovered. And remarkably, it was published only a few months. This is January 1916. It was published only a few months after the Einstein equations were first written down. So this is Schwarzschild. You see him here. This is an excerpt from his paper. And again, there's all this German here, which I don't understand, so I removed it. And if we look at this expression here, this is the celebrated Schwarzschild metric. And if you are fast enough with computations, then you can quickly convince yourself that this metric is indeed a Ricci flat. That's to say, it is indeed a vacuum solution of the Einstein equations. Okay, and well, you'll notice that this metric is spherically symmetric and it's stationary. So in some sense, if you impose those symmetries and you write down the Einstein vacuum equations, it's not that hard, although it's not completely trivial to sort of derive this expression. And that's precisely what Schwarzschild did. Okay, so I've rewritten it with the one difference that I've changed what was written there as A to 2m. So this is actually a parameter. So this is actually a family of spacetimes that depends on this parameter. Actually, if this parameter is equal to 0, then this is simply the Minkowski metric in spherical polar coordinates. You can actually consider this parameter also to be negative, but I will only consider the case where this parameter is positive. So we should think of this as a one parameter family of solutions where the parameter is positive. And if you just stare at this thing, you don't even need to understand anything other than sort of algebra, you immediately recognize that this expression looks problematic at 2, and actually, well, strictly speaking, at 3 places. So at r equals 0, this looks problematic because, well, here you see 2m over r. That blows up. Well, so it looks like this expression here, this coefficient is blowing up. If you look at, let's say, r equals 2m, then, well, this coefficient here vanishes. That's not necessarily bad in Lorentzian geometry. But if you look at this coefficient here, well, so the denominator vanishes, so 1 over this blows up. So it looks like there's something wrong with the coefficient of this part of the metric. And well, strictly speaking, if you didn't know any better, then you might also say that I don't like this expression here when theta is equal to 0 or pi, because it looks like this is degenerating, and then this metric is becoming degenerate. Well, of course, no one ever said the last statement, because everyone knows that when we write coordinates like this, actually the underlying manifold that we have in mind is not the theta phi plane, but it's actually the sphere covered by theta phi coordinates, which of course the coordinates themselves degenerate at the poles. So no one was ever confused by the metric at theta equals 0, pi, because everyone always knew that this is just a spherical metric. But it turns out that people were very, very confused about what goes on at r equals 2m, even though the resolution of that issue is in fact exactly the same as what was going on here. Namely, the fact that this is blowing up is simply because of the coordinates chosen. And this whole issue was very, very confusing because these debates in some sense took part before the notion of differential manifold was formalized. So anyway, we don't have to revisit those old stories because in some sense the solution to that is very, very simple. If you define a new coordinate by the Greek letter tau, okay, and this is defined to be t plus some well-chosen function of r that I'm not going to write down, okay, then you can rewrite the metric in this form. And if you see sort of just by inspection, the metric in this form is regular for all positive values of r. Okay? It is still singular in this form at r equals 0. And it turns out that the singularity at r equals 0 is essential. I'm not going to talk about that. So how to understand this metric? Well, it's sort of general principle in general relativity. If you want to understand the metric, then what you should do is you should draw the light cone. So remember, for a Lorentzian metric, you should think that at every point there's an infinitesimal light cone that you can draw. Okay? So this is just the set of all tangent vectors at the point that have length 0 with respect to the metric. So what you should think is that when you're very far away, so very far away means large values of r, okay, then the light cones, they look like the Minkowski light cones. They're basically more and more upright. But as you go towards lower values of r, these light cones, they're beginning to turn in. And you compute, you see that at exactly r equals 2m, so this is r equals 2m in this picture, this cylinder, okay? The light cone is tangent to r equals 2m, so it has completely turned as depicted. And you can see this from the form of the metric because this coefficient here vanishes. What does that mean? That means that the coordinate derivative d by dt is null, which means that the coordinate derivative d by dt is sitting on the light cone. Okay. And if you go further in, then it turns out that the coordinate derivative d by dt is outside, or d by d tau, I should say, is outside the light cone. So it looks like this. So one of the morals of this story is that just because a coordinate is called t or tau does not mean that the coordinate derivative d by that coordinate is pointing in a time-like direction. Okay. So this is the geometry of Schwarzschild. And so now what is the significance of this r equals 2m in view of this property? Well, we can say the significance easily in terms of observers. So imagine now that we have two observers depicted here. So this world line, so this is this blue world line, okay, and this other world line, this purple world line, okay. So imagine this blue world line stays away from r equals 2m for all of his or her proper time, whereas the purple world line crosses r equals 2m. So as long as the purple world line is outside of r equals 2m, then he or she can send a signal, that's to say, the trajectory of a light ray to the observer, to the blue observer, okay? Because these signals, they travel on trajectories which are everywhere tangent to these light cones. Okay? But if you notice, once this observer has crossed r equals 2m, then any signal that they send, because the light cones have turned in, is directed always to smaller and smaller r values. So in particular, it can never go outside of r equals 2m, and it can never reach this observer here. So for this reason, we say that this region here, the region r less than equal to 2m, is a black hole region. It is precisely a region that cannot communicate to observers outside, particular to observers which are very, very far away. So it's as simple as that. That's what a black hole is. And this Schwarzschild geometry, the first non-trivial explicit solution of the Einstein vacuum equations to be written down, it secretly exhibited this phenomenon. And I should say that sort of this aspect of the Schwarzschild geometry was first understood by Georges Lemaitre in the early 30s. Okay, so there's one last thing I want to say. This is not essential for understanding the rest of the talk, but in order for someone to be a true relativist, they have to have some nodding acquaintance with what are known as Penrose diagrammatic depictions. And I'll use these depictions later on in the talk, at the very least as pictures. So I want to sort of say a few words about how, as relativists, we typically draw spacetimes. So this is the Schwarzschild spacetime as I described it just now to you. And it turns out that the picture that we typically draw as relativists is this picture that I've drawn down here. So let me very, very quickly tell you how you can pass from the picture that I gave you to this other more abstract and more useful representation. So because this is a spherically symmetric spacetime, I can first suppress completely the I can suppress completely these spheres. That's to say, I can, let me just think about, have r equals 0 here. I have r equals 2m. Okay, and I can just suppress those spheres. So let me redraw this very quickly so you can see. Okay, so I'm just going to draw the cones, but I'm going to draw the radial, if you want, null directions. Okay, so these are x's now. Okay, so I've just done that, nothing else. So then what you notice is the following. You can actually change, so this is now a two-dimensional picture here. So you can now change the coordinates so that all the cones are actually aligned with the usual cones of flat two-dimensional Minkowski space. Okay, so actually this is the Lorentzian analog of uniformization theorem, but in fact, in some sense, it's a much easier than the Riemannian version of that. And if you think about that, if you change the coordinates so that you make so I've just changed coordinates here. I passed to this, and now I pass to this here. So if you change coordinates so that the cones look like that, then you'll notice that r equals 0 now will look like this. Okay, I should make this. Because remember, the cones here were pointing this way towards r equals 0. So r equals 0 will look like this. And r equals 2m will be tangent to the cone. So r equals 2m will look like this. So there's one last thing that we can do, and the one last thing that we can do is we can further rescale our coordinates so that we bring in infinity into somewhere finite. And that's actually what I've done here. Okay, I've just rescaled the coordinates so that infinity is somewhere finite. So finally, I have a depiction of space-time, or rather the sort of the quotient of space-time by the action of the special orthogonal group, such that the radial null directions are all at 45 and 135 degrees from the horizontal. Okay, but moreover, infinity has been brought somewhere finite, so I can attach infinity as a finite boundary. So this finite boundary is what's known as null infinity. Strictly speaking, actually, future null infinity. And this is a very useful concept that I'm not really going to use in this talk, but you should really think that this is where gravitational radiation, so the gravitational waves that we now directly observe on Earth, well, in the mathematical model, you should think that that gravitational radiation lives on this boundary, future null infinity. So in any case, what's very nice about these depictions, if you learn to love them, is that you can read off by sight the what's known as the causal geometry. So in particular, let me draw these two observers that we had above. So let me draw these observers here in this picture there. Well, it's very easy. So so this observer here looks something like that, and this observer here looks something like this. And now it's very easy to, in this picture, to understand what signal propagation looks like, because signal propagation is always at 45 degrees. Okay. So in particular, one sees immediately that it is precisely this region of space-time which is not visible to this observer. And in some sense, the more sophisticated way of saying it is that this region of space-time is not in the past of this future boundary null infinity. Okay. So in any case, this is the type of depiction of black hole geometry that you learn to love if you're a relativist. And I will often illustrate spacetimes by pictures like this. And in any case, even if you don't follow everything I said in order to construct this picture, you should remember that it's really not so difficult. And in particular, this picture encodes non-trivial information about the sort of causal relations of points. That's to say, which points can send signals to which other points. Okay, and in particular, which points can send signals to it. All right, so that's all I want to say about Schwarzschild. So now I'm going to talk about the nonlinear stability of Schwarzschild. So, so again, the question is the most basic question that you could possibly pose about dynamics of the Einstein equation in a neighborhood of the Schwarzschild solution. So you can think of the Schwarzschild solution itself in terms of Yvonne Choquet-Bruhat's theorem as the unique solution of the Einstein vacuum equations that arose from what I'll call Schwarzschild initial data. Right? So in this picture, actually, these what I just depicted in yellow are two null cones emanating from a sphere. Okay? And you can think of that as initial data, the geometry on these cones, you can think of as initial data for the Einstein vacuum equations. And you can think of the Schwarzschild solution as the solution that arise from Schwarzschild initial data. Okay? So once you say it in this language, then the stability question is simply the following. Suppose I slightly perturb this data. I don't know how to draw that. Okay, and I solve the Einstein vacuum equations, as Yvonne Choquet-Bruhat told us that we could. What happens? What happens to the solution? Does it have anything to do with the Schwarzschild solution? Does it even sort of exist for, quote, all time, whatever that means? This is the stability question. And the sort of first version of the main theorem that I want to discuss, and this is forthcoming joint work with Gustav Holzhegel, Igor Rodnyansky, and Martin Taylor, is that the Schwarzschild family is asymptotically stable in evolution. Okay. So what does that mean? So let me sort of be very precise. So it's asymptotically stable in evolution under the fully nonlinear Einstein vacuum equations. So the equations reach equals 0. No symmetry assumptions on the initial data. So I'm looking at fully general initial data. And the stability statement refers to the black hole exterior. So what I'm saying is that this region here of the Schwarzschild solution, which is the outside of the black hole region. So again, you can think of this as characterized as the points of spacetime that can send signals to faraway observers, or in the more sophisticated language, to future null infinity. This region is asymptotically stable. Okay, so I said that this is the theorem, but if you know anything about general relativity, you know that this theorem, as I stated it, could not possibly be correct. There must be something I'm forgetting. So the actual theorem is that this is true modulo one thing. And what's this one thing? This one thing is the celebrated Kerr spacetime. Because if you know your general relativity, you know that in 1963, it was discovered that Schwarzschild is actually a one-parameter subfamily of a two-parameter explicit family of Einstein vacuum solutions, okay? Which are only a little bit more complicated, but were much more difficult to derive if you didn't know they were there, and which were found by Roy Kerr. So these actually, so this is a two-parameter family. The parameters are M and A. This family of solutions is less symmetric than Schwarzschild. That's why it was difficult to find. It's still stationary, but it is only axisymmetric. It is not spherically symmetric. Okay, and this extra parameter, which I'm denoting A, okay, is a rotation parameter. So A times M is a measure of the total angular momentum of this black hole, whatever it means. So if you know that you have a one parameter family of stationary solutions, which is simply a one parameter family, a one parameter subfamily of a larger two parameter family of stationary solutions, then the best that you cannot expect that the one parameter family is asymptotically stable. The best that you can expect is a finite codimension asymptotic stability result. And what's that codimension? Well, naively, you might think that this is a one parameter family. The Schwarzschild is a one parameter subfamily of Kerr, so you should expect sort of a codimension 1 asymptotic stability result. But actually, secretly, if you want to parameterize smoothly the moduli space, because this Kerr solution is less symmetric than Schwarzschild, you have to over-parameterize Kerr. So you should really think of a Schwarzschild as a codimension 3 family of solutions in the Kerr family. Okay, so with this in mind, let's return to the theorem, and the statement is that indeed the best, the most stability that could possibly hold for Schwarzschild indeed holds. That's to say, the Schwarzschild family is asymptotically stable in the black hole exterior for the full expected set of perturbations. That's to say, there exists a codimension 3 submanifold in the moduli space of vacuum initial data sets containing the Schwarzschild family, such that for this submanifold, you have asymptotic stability of Schwarzschild. And what does asymptotic stability mean? Well, for the more experts here in the audience, it means, first of all, you possess what's known as a complete future null infinity. That's to say, faraway observers, if you want, observe for all time. You can think of this as an analog of global existence that I mentioned in passing earlier. And the past of this future null infinity, which again, if you learn to love these representations, you can read off from this picture. It's exactly this region here. This past, so you should think of this as the black hole exterior, is indeed a black hole exterior. That's to say, it is bounded to the future by sort of a hypersurface, which you should think as the analog of this R equals 2m hypersurface okay, and which we call this the event horizon. And moreover, this has sufficient regularity and it's future complete. Moreover, the solution remains globally close to the Schwarzschild metric here. Okay, so in the exterior, the solution stays close to Schwarzschild, and finally it asymptotes. And this is the sort of asymptotically stable part. It asymptotes back to another member of the Schwarzschild family. Remember, Schwarzschild is still a one-parameter family of solutions, as a suitable notion of time goes to infinity. And again, what does time going to infinity mean? If you learn to love these pictures, it means as you sort of go in this direction here, in this time. So if you want, you can think of these three statements with the following labels. So that this first statement is known as weak cosmic censorship. Okay, so the first statement is that weak cosmic censorship holds in the neighborhood of Schwarzschild. So weak cosmic censorship is actually the more general statement that for generic initial data, complete future null infinity is complete. Okay, so statement one is actually conjecturally true for generic initial data for the Einstein vacuum equations. This is one of the great open problems in general relativity. And the second statement you should really think of as being the statement of orbital stability. This is the statement that Schwarzschild is orbitally stable. The metric stays close to Schwarzschild for all time in the relevant region, the black hole exterior. And the third statement is the statement proper of asymptotic stability, namely that you asymptote back to the Schwarzschild metric. Now, you might say we would be very happy to prove just one or 1 and 2. After all, statement 1, conjecturally, it's true for generic initial data. Statement 2, conjecturally, and we'll get back to this later, orbital stability of Schwarzschild, it should be true without the restriction to this codimension 3 submanifold. But in practice, and this is just a fact of life in the theory of nonlinear wave equations, these three statements, they come as a package. So if you don't prove asymptotic stability of something, then you cannot prove 1 or 2. So you really prove all these things at the same time. And I'll say a few words in just a second about the proof. So these really do come as a package. And since clearly restricting to codimension 3 is a necessary condition to have asymptotic stability, then of course this necessary condition then is inherited in the proof for the other statements. Okay. So that is the statement. Okay. So let me say immediately some previous work to put this into perspective. So first of all, work without symmetry. So in some sense, the flagship result in this field is the nonlinear stability of Minkowski space, the first space-time that I discussed in this talk. So even this is a highly non-trivial problem, and it remains the only asymptotically flat space-time that has been proven to be nonlinear stable in general relativity. So this was originally proven by Christodoulou Kleinerman in 1990, and there was a new and very different proof by Lindblad and Rodnyansky in 2004. Okay. So I'll maybe refer to this again later on. So there's been various works in symmetry classes. So of these works, let me just highlight one thing, which in some sense is quite recent and is the most impressive of these works. And this is recent impressive work of Kleinerman and Sheftal, where they proved nonlinear stability for four-dimensional Schwarzschild spacetimes in what's known as polarized axisymmetry. Okay. So this is the first nonlinear stability result beyond 1+1, and this already has several of the difficulties of the full problem. Okay. So this is previous work, and because in our theorem we incorporate all solutions which asymptote to Schwarzschild, then this set of symmetric solutions are actually, they are contained in this codimension 3 set. So if you want, this result is also contained in our theorem. Okay. And finally, I'll mention this at the very end of the talk, hopefully, but I just want to mention very quickly now, there's an analog of this problem in the case of positive and negative cosmological constant cases. And in the positive cosmological constant case, there's nonlinear stability of de Sitter. This is actually a much easier problem than nonlinear stability of Minkowski space, and was proven previously by Friedrich. And there's nonlinear stability of very slowly rotating Kerr de Sitter. I'll mention this later on by Hinz and Vassen. So this is a very nice recent result from a few years ago. Okay, so let me say a few components of the proof. It's proofs in this subject, unfortunately, are long, so it's difficult for me to give the whole proof in the context of this talk, but I'll try to at least identify some of the components that play a role in the proof. So the first component is the notion of double null gauge. So in general, in order to do anything in analysis of the Einstein equations, you have to choose a gauge in which the equations are indeed hyperbolic and well-posed. So one example of such a gauge is harmonic gauge. This is what Yvonne Choquet-Bras used to prove well-posedness. This is what Lindblad and Rodnyansky used to prove stability of Minkowski space. But another type of gauge is something known as double null gauge. And this really has been used by Christodoulou and by other people in many works in the past 20 years. So what is this gauge? Let me just say a few words, because it's very much related to the null cones with which this talk began. So in this gauge, you first, let's say, choose a sphere. So this is a two-sphere in space-time. And then you consider it's the boundary of its future, and the boundary of its future consists, at least locally, of two null cones emanating from the sphere. So you can think of one as outgoing, whatever that means, and the other is ingoing. And now we can go further. So we can now foliate, let's say, the outgoing null cone by spheres, and we can foliate the ingoing null cone by spheres. Okay. And now we can look at the ingoing null cones coming from these spheres. And we can look at the outgoing null cones coming from those spheres. And lo and behold, we have a double null foliation of our spacetime. So we have a spacetime, we have a foliation of spacetime by ingoing and outgoing light cones. So it turns out that you can also talk about a so-called null frame associated to this double null foliation. So you have a pair of null vectors which you can normalize in various ways. And now you can sort of incorporate the information of the Einstein equations. Remember, the Einstein equations are the statement that the Ricci curvature equals 0 as the structure equations of this double null foliation, together with the so-called Bianchi identities for the curvature, where you also plug in this relation. And moreover, you can express these Bianchi identities. You can decompose the curvature tensor, and you can express these Bianchi identities where the curvature is expressed with respect to this double null frame. So if you do that, you obtain a very ugly system of equations, very long system of equations, but it's a very geometric system of equations. And that system of equations is well posed. And this is, it turns out, a very fruitful way of trying to understand the Einstein equation. So this is one of the aspects of the proof. Okay. Second element of the proof is a linear stability result in double null gauge. So so in order to prove a nonlinear stability result, you certainly need to first prove a linear stability result. And because you're going to have nonlinear terms, then it's very important not only to prove linear stability, but also to prove inverse polynomial decay, so to prove that things decay fast, sufficiently fast. And moreover, and maybe I'll say a word about this later, it's very important that you prove this using energy estimates, or in any case, it's very useful if you prove this using energy estimates. And we'll see that in just a second. So this was actually a result obtained previously in a paper with Holzigel and Rodniansky. And it turns out that this linear stability result already had to face several fundamental difficulties. So it turns out that the difficulties are as follows. So the first thing that you need to do is you needed to identify gauge invariant quantities and show quantitative decay for those gauge invariant quantities. And turns out that there's a very well-known gauge invariant quantity. In fact, it's precisely a curvature component expressed appropriately in this double null frame, which satisfies what's known as the Zakoro equation. This is an equation that was identified by Tucholsky in important work in the 70s. And via using some transformation that's inspired by Chandrasekhar, we were able to reduce this to showing appropriate results for the scalar wave equation on this background. And now the study of the scalar wave equation on black hole backgrounds has been something that in the last 15 years there's been a lot of work on, and in some sense has been completely or almost completely understood. Many people have actually worked on that problem, some of the names listed here. So this is one aspect that feeds in to the linear stability problem. And in fact, a lot of the interaction between the geometry of the black hole exterior and the analysis already happens in A. So a lot of the interesting interplay between geometry and analysis is already in A. But there's more that you have to do. So starting from these so-called gauge invariant quantities, then you have to sort of prove estimates for the whole system of linearized gravity written in whatever gauge you have. So in particular, in our case, in double null gauge. And finally, and this is an interesting point that I want to emphasize, which in fact should be clear from when I first discussed double null gauge. In double null gauge, you first have to pick a sphere. So you pick a sphere, and then you look at these null cones, okay? But somehow you have to first pick this sphere. And it turns out that if you want to do an asymptotic stability problem, and you want your spacetime to approach a known spacetime, you actually have to pick this sphere teleologically. So you don't pick this sphere in the present, you actually pick this sphere in the future. And how to correctly normalize this choice of sphere and actually other normalizations that you have to do, this is something that actually you already see in the linear stability problem. And it's one of the big new difficulties of proving linear stability of this spacetime. Okay, so once you've done all this work, then you actually have to do the nonlinear problem. And there are serious additional nonlinear difficulties that arise. In particular, you have to capture what's known as the null condition. So this was something that was studied very much in the 70s and 80s in the theory of nonlinear wave equations. And one good thing about double null gauge is, in some sense, it automatically incorporates in a nice way this null condition. But there are also some other difficulties. You have to identify the Kerr parameters teleologically in addition to constructing the gauge. And you have to adapt all of these constructions that you do to a complicated nonlinear bootstrap setting. So it's a serious difficulty to do this in the full nonlinear theory. On the other hand, because the linear results are proven using energy estimates, this is one of the nice things about energy estimate-based proof. You can immediately directly apply those energy estimates directly to the nonlinear problem. Okay? So the structure of the full nonlinear statement really follows closely with the structure of the linear proof. Okay, so let me just say very quickly what the full black hole stability problem is. Well, the full black hole stability problem is simply to replace Schwarzschild with the Kerr family, okay, and prove asymptotic stability for the Kerr family in the full subextremal range of parameters. So this is the full range of parameters where the Kerr geometry indeed represents a black hole. And of course, there are many additional issues that come up in going from the Schwarzschild result to the full Kerr result. Some are more of a technical nature, but there are many other issues. And in fact, perhaps the most interesting issues that come up when you pass from Schwarzschild to Kerr, they're something called superradiance, which really has to do with what's going on in sort of the large A regime. So when A is in principle close to extremality. And you already see this problem if we go back here, in the sort of part A of the proof of the past theorem that I said. That's to say, you already see this issue when you try to look at gauge invariant quantities in linear theory and try to prove decay for them. So it turns out that this problem has been completely resolved in linear theory in Kerr for the full subextremal range. So this is joint work of Yakov Schlapentoch-Rothman and Rita Teixeira da Costa. So they've proven that sort of solutions of the Tucholsky equation, which governs gauge invariant perturbations, remain bounded and decay polynomially. Okay, so in view of this latest result, then I think a complete solution of this problem is very feasible. Okay. All right, so very, very quickly, let me say a few words about the case of non-zero cosmological constant. So let's return to our crash course on general relativity. So these were the Einstein equations as they were written in Einstein's original paper. But Einstein was somewhat apt to change his mind. And 2 years after writing that paper, he wrote another paper, which you can see here the title page of. And in this paper, he made a little modification to his vacuum equations, which you can see here. And the modification is precisely in this term here. So he added the possibility of having an extra term, let's say on the left-hand side, okay, which is proportional to the metric with some constant of proportionality lambda, which is now known as the cosmological constant. So according to this modification of the equations, then not only matter, not only space itself, but also this cosmological constant that now we typically denote with capital lambda, this can also curve space-time. So it turns out that these modified equations, so these modified equations are interesting on the cosmological scale, on the very, very large cosmological scale, where it is thought that lambda, you should take lambda to be a very small positive number. But they are also interesting in the context of speculations in high energy physics, where it's actually the lambda negative case, which is of interest. And there are analogs of the Kerr solution for both positive and negative lambda, which were worked out by Brandon Carter. And the metric takes this form. So these solutions are typically referred to as Kerr de Sitter or Kerr anti-de Sitter, but they're actually due to Brandon Carter. So you can ask similar questions about black hole stability for these Kerr de Sitter and Kerr anti-de Sitter spacetimes. So very, very quickly, let me first discuss the easy case. So the easy case is when the cosmological constant is positive. And in this case, it's been proven by Hinz and Vasi that the sort of the analog of the black hole region, exterior, which is the region here, if you can read these diagrams, is indeed non-linearly stable, at least in the very slowly rotating Kerr de Sitter case. And the reason this problem is easier than, let's say, the asymptotically flat case is because not only is this stable, but one has very, very fast exponential decay to Kerr de Sitter, as opposed to inverse polynomial decay, which is the best that you can have in the asymptotically flat case. Now, it's still an open problem to understand what happens in in the general Kerr-de Sitter case, so the case which is not very, very close to what's known as Schwarzschild-de Sitter. And in particular, even the linear stability, even the linear modal stability of such spacetimes is an open problem. So that's a very interesting open problem that remains in this case. But in some sense, the more mysterious case is the case where lambda is negative. And so the case that lambda is negative, the geometry of spacetime in these depictions look like this. And actually, one of the interesting things about negative cosmological constant is that the boundary at infinity is now time-like. So you actually also, in addition to posing initial data, you also have to pose boundary conditions at infinity. So as I mentioned in the context of the proof of the nonlinear stability of Schwarzschild, a lot of the difficulty of the problem is already incorporated in studying the wave equation and its decay properties on a fixed background. And there was a remarkable theorem of Holzigel and Smolevisi from several years back now, and they showed that general solutions of the wave equation on this exterior, so the exterior region is here, they do decay as you go forward in time, but they only decay inversely logarithmically, and moreover, that really is a sharp rate. So that's their theorem. And on the basis of this theorem, they actually conjectured that, well, inverse logarithmic rate of decay is very, very slow. It could be possible that at the nonlinear level, nonlinearities build up in time. And as a result of that, conjecturally, and this is the conjecture of Holzigel and Smolevisi, the Kerr anti-de Sitter family is nonlinearly unstable. And this is a very interesting conjecture, because this truly would be a purely nonlinear effect. You would have a weak form of linear stability, but at the nonlinear level, you would have instability. And this can be compared with actually a recent theorem of Yorgos Moschidis, who showed that pure ADS spacetime is indeed nonlinearly unstable in the context of Einstein-Mather systems. So somehow, I think this type of question is really one of the most interesting sort of future directions in the sort of mathematical study of general relativity, because here is a setting where nonlinear PDE, in particular, really nonlinear analysis, can say something fundamental and surprising about black hole solutions that people in theoretical physics care about very, very deeply. Okay, sorry to have gone a few minutes over, but with that, let me end. Thank you.
Okay. Thank you. It was a wonderful and very clear talk. So I have a question. So I think that you have a result concerning also the nonlinear instability of the Kerr solution in some range of parameter. Is there any kind of result on concerning the instability of the Kerr solution?
No, not so. So no, I mean what. So there are two senses in which there are instability results connected to Kerr. So first of all, there are instability results which are connected to the black hole interior. So in the black hole interior, it is conjectured that at a high level of regularity, at least, one has instability towards the Cauchy horizon. Actually, that has not been proven for the vacuum equations, but this is sort of conjecture. But as far as the exterior is concerned, then for the Einstein vacuum equations, the conjecture is that the solution is stable. But for instance, if you consider a massive Klein-Gordon field on a Kerr background, then it has been proven actually relatively recently by Schlappendorff-Rothman that solutions grow exponentially for certain parameters of the mass. So this suggests that although Kerr is stable in, let's say, for the vacuum or for some classes of suitable matter, There are matter models that are not incredibly exotic. So having a massive Klein-Gordon field is not the most exotic thing you could think about, for which you actually have instability. So there are instability results of that.
Okay. So I have a question from the chat on YouTube. It's the following. I don't know who posed the question. The Schwarzschild horizon bounds a trapped region with a curvature singular inside. Can the same be said for the perturbed solutions? Does a singularity exist also for perturbed solution?
Yeah, so it's a very, very good question. And in fact, so let me say, first of all, that one of the nice things about, so can you still see my screen, by the way, because I can't actually.
Yeah, we can see.
So let me go back to this depiction of the Schwarzschild. Let me go. Maybe I'll say it with reference to the theorem. That recall that in the statement of the theorem, I'm really only telling you anything. I'm only telling you stability about this region, the region outside the black hole. And indeed, as was just said, if you look at the Schwarzschild solution, as I showed you, then, so this is a trapped surface, actually, in the language of the question. So in this depiction, this is precisely trapped surface. And here is the R equals 0 singularity of Schwarzschild. So, so this theorem does not say anything at all about what's going on inside the black hole. But there is another result, actually, which is joint work with Jonathan Luke, which is the following. If I have any space-time which along its event horizon is converging, okay, to Kerr, okay, if along the event horizon is converging to Kerr, then I know that the analog of this Penrose diagram depiction of the space-time in the neighborhood of the event horizon will look like this. So in particular, it will not be bound by an R equals 0 singularity. It will be bound by what's known as a Cauchy horizon. And the Cauchy horizon may or may not be, let's say, a curvature singularity, but it is not too singular. So there's a sense in which it has some amount of regularity. Now, conjecturally, it is actually a curvature singularity. In fact, it's a little bit worse than a curvature singularity. So if that is true, then in the case of spacetimes that approach Kerr, you will have a little bit of curvature singularity inside the black hole. So if you put together, that's to say, all these things. However, and I have to stress this, our theorem with Jonathan Luke, when I say that the spacetime approaches to Kerr, I really mean rotating Kerr. Let's say, I really mean that it approaches Kerr and not Schwarzschild, not in the sense where Kerr includes Schwarzschild. And in fact, in the special case where my spacetime approaches Schwarzschild, which is exactly the case of our theorem, okay, there is no relevant analysis of what happens inside the black hole. So, so in particular, one cannot say, and it really has not been studied at all, what the sort of geometry of the black hole interior would look like for the solutions constructed in our theorem, even just in the neighborhood of this point of the Penrose. The one statement that we can make, and actually it's interesting, but it's a relatively soft corollary of our theorem, is that the supremum of curvature in the black hole interior will be infinite. So it's a funny thing that you can actually infer this rather softly. So in that sense, there is something singular about the black hole interior, but it's really only that statement, that the supremum of curvature measured in some way is infinite.
I see. So I have a question. So suppose you have a charge, so that you're talking about the Kerr-Newman solution.
Yes.
So And the other question would be if you add matter, like if the stress energy tensor is not zero.
So those are great questions. And so let me first address Kerr-Newman. So actually, Elena Georgi has done various work on Kerr-Newman. So first of all, she has proven the linear stability of Reisner-Nordstrom. So generalizing the results on linear stability of Schwarzschild. And she also has some results on Kerr-Newman. Again, it's very interesting that even the mode stability of the Kerr-Newman solution for general values of the parameters is unknown. So it's really, I mean, even at the linear level, even at the level that's sort of, in principle, even the question of whether there exists exponentially growing solutions of the linearized equations around Kerr-Newman. So the relevant equations are now called the electrovacuum equations, or Einstein-Maxwell equations. This is open. And of course, in some sense, the Einstein-Maxwell system is one of the closest analogs of the Einstein vacuum. So when you add matter which are more different than the vacuum, then the situation becomes more and more complicated. So one popular matter model that has been discussed in recent years is the Einstein-Vlasov system, both massive or massless. So this can be thought of as modeling collisionless particles in the massive case, and well, in the massless case, sometimes even used to model neutrinos or something like that, even though they're not, strictly speaking, massless. And so, for instance, for such matter models, there have been recent results on stability of Minkowski space by various groups, by Zmilevici and collaborators, by Lindblad Taylor. So there's been a lot of work in that direction. And in principle, one can certainly try to study the problem of black hole stability for those models. There will be, especially in the massive Vlasov case, there will be some very, very interesting features of that problem, because you can no longer expect to have asymptotic stability. So I think that's certainly a very, very interesting problem, which is something for future research.
Okay, thank you. So is there any other question from the room? So if not, I mean, I would thank again Professor Michalis Theorems for this great talk. So I should close the session. Professor Moscariello, she's the Vice President of the INdAM. So thank you. Okay. There she is. Please.
Okay, good evening. Just a few seconds for conclusion of this day, the first part of the INdAM day. The pandemic just changed the organization of this event. Really, the high profile of the speakers to talk on topics of great interest tell us that just pandemic changed the organization, because the spirit and the purpose of this day is the same. Everything was well. Then I thank the speakers for accepting to be with us today and for interesting talks. And I hope to meet them in person as soon as possible. Many thanks to the President for who enthusiastically supported this event, and also the Scientific Council that with me strongly wanted that this event is not cancelled. And Also, again, also many thanks to the administrative and the technical staff of INdAM. And thank you very much to all of you for your participation. And I hope see you tomorrow for the second part of the INdAM Day. Good evening and see you tomorrow at 10 o'clock.